Welcome back to the Automotive Electronics course. Okay, let's see. You finished everything. Now, being a certified graduate of the entire course, you can review any topic. Just select the topic you'd like to review. Welcome back. Okay, let's see. You finished everything up through anti-lock brakes. Now you can review any topic you've completed or go on to steering and suspension.
Hi, you're back. So, you've gone through steering and suspension. Now you can go over any topic you've completed or go on to ignition systems. Welcome back to the Automotive Electronics course. Let's see, you've finished everything up through ignition systems.
Now you can review any of the topics you've completed or continue on with fuel control.
There you are. Where were we? Oh, right. You've mastered everything through fuel control. Now, if you'd like, you can review any topic you've completed or go on to transmission and multiplexing. Okay, you've finished steering and suspension. You know what to do. Review any topic you've completed, exit the course, come back later, or continue on with ignition systems.
Okay, you've completed ignition systems. Now you can review any topic you've completed, exit and come back later, or continue on with fuel control. Great, you're done with fuel control. Once again, you can review any topic you've completed, exit and come back later, or go on to transmission and multiplexing. Wow, dude, that's some driving. Don't try this at home. You should only drive like this if you race Indy cars or do Hollywood stunts for a living.
Or drive a cab.
Yeah, that too. As you can see, for maneuvers like these, power steering is a must. So the first thing we'll cover is steering system operation. We'll look at optical sensors and stepper motors. After that, we'll move on to electronically controlled suspension, trim height adjustment, and shock damping.
And then we'll finish up with a steering system troubleshooting exercise.
Okay, so let's start with the relationship between vehicle speed and steering assist. Okay, here we have a constant positive 5-volt signal on the output. Now this isn't looking very good. Which of these conditions would cause a constant positive 5-volt signal? Select them all, then touch Done. Right. Output signal frequency varies with the rate of steering wheel rotation. The signal goes to the controller, then the controller processes the signal and sends it to the actuator, which in this case is a stepper motor.
Seems like a perfect cue to look at stepper motor operation.
Right you are. Step right up, folks, for the stepper motor tour.
You probably already know how a DC motor works. Direct current induces opposing magnetic fields in the field coil and armature. DC motors can provide single-speed, two-speed, or variable speed operation. But some applications require more precise control.
The electronically controlled suspension performs two basic functions. It maintains vehicle height at a preset level, which we call trim, and it switches between a soft ride and a firm ride.
To understand the system, you need to know the components. Let's start with those sensors.
Trim height adjustment maintains the vehicle at a level position. What will cause trim height to be adjusted? A panic stop, a high-speed turn, quick acceleration, or a heavy load. Make your choices, then select Done. The pneumatic leveling system was designed to slowly accommodate for long-term conditions, like an abnormally heavy load in the trunk. But the system ignores transient situations, like hard stops, turns, or accelerations, to prevent unwanted leveling. For each of these driving conditions, different sensors provide input to the controller to maintain a stable ride. In some cases, more than one sensor provides an input. Match all the driving conditions with the sensor or sensors that provide information. Select the sensor or sensors that provide input to the controller as a result of that condition. When you've made all your matches for each condition, touch Done.
Now let's take a look at the dual damping actuator. Now, this is an interesting little device.
Right. It's related to the stepper motor, but it's used to control shock absorbers in the suspension system.
It switches the shock and strut settings according to driving conditions, from a soft luxury car mode to a firm high control mode, or vice versa.
Well, we've covered the electronically controlled suspension system.
Next, we'll bounce back to the steering system and apply some of the things we've learned.
Wow. We sure covered a lot in this section.
You know, Tom, we did. We took a turn with steering systems, saw the light on optical sensors.
All right, enough. Thank you. We also looked at stepper motors, electronically controlled suspension, including trim height adjustment, and dual damping actuators.
So, now you know what it takes to keep from wearing your coffee when you're four-wheeling it over the sidewalks to get to work on time.
So long for now.
And 5, 4, 3, 2, 1. Ignition.
Not that kind of ignition.
Sorry.
The kind of ignition that ignites the fuel in an engine?
Right, yeah, okay. In this section, we'll take a look at the basics of ignition system operation, and then we'll focus in on some of the components, like the magnetic or variable reluctance sensor, Hall effect sensors, knock sensors, and ignition coils.
When you're looking at an ignition system, keep one thing in mind.
No matter how complicated they seem, all ignition systems perform the same basic function. They get the spark in the right place at the right time, so you get the most bang for your buck.
It's as simple as that. So to keep the ignition system running, we use sensors to measure crankshaft position and engine speed.
We also need some sort of electronic module to control the spark, and an actuator to deliver a high voltage to the plug.
Let's look at how some of these components work.
We'll start with the Hall effect sensor. It's used on TFI-4 and DIS ignition systems and in other vehicle systems. Another sensor that many ignition systems use to measure rotation is the magnetic or variable reluctance sensor.
It was used on the DuraSpark systems back in the 70s.
And it's used on EDIS systems today. In the EDIS system, the reluctor or trigger wheel is mounted on the crankshaft. It has one tooth every 10 degrees and provides a very precise high data output. One tooth every 10 degrees would make 36 teeth, but this wheel has one tooth missing, making it a 36 minus one tooth wheel. That space sends a slightly different signal, allowing the control module to get a precise fix on the position of the number one piston. The ignition system uses that signal and the series of pulses that follow to infer the position of all the other pistons. The frequency of the pulses also provides information on engine speed. Once the ignition system collects its information on crankshaft position, engine speed, and timing modifiers, it needs to make some decisions about exactly when to fire the spark, and then it needs to fire it. The PCM and the ignition control module work together to make it all happen. The knock sensor is specially designed to sense spark knock and send feedback about ignition timing to the powertrain control module.
Now, you won't see one on all vehicles, but would you know one if you saw one? So that's how piezoelectric sensors work.
And I'm about to check this one. If I tap it against the desk 3 times, we should see a normal knock sensor output. What do you think it'll look like? Select the waveform you'd expect to see from a properly operating knock sensor.
We've seen the sensor and processing power that electronic ignition systems use to control the spark. Now it's time to look at the business end of the ignition system, the ignition coil.
Ignition coils are really nothing more than transformers. They take battery voltage and transform it into 40 to 50,000 volts. That's enough to jump the gap in the spark plugs and ignite the fuel. Here's how they work. In distributorless systems, the single coil and distributor have been replaced by a coil pack and something called a waste spark system. To control ignition system operation and correctly time the spark, the sensors, PCM, ICM, and coil pack pass a lot of signals back and forth.
In fact, your next task is to troubleshoot a problem using just those signals.
Like we said, ignition systems change pretty rapidly, but we've covered the basics of ignition system operation and the main components, like the variable reluctance sensor, Hall effect sensors, knock sensors, and ignition coils.
And as long as you know the basics, you can always pick up on a new system.
Right. Do you suppose maybe I could have my rocket back now, please?
Yeah, I suppose so.
Thanks. Fuel control is based on maintaining the correct air-to-fuel ratio. The optimal air-to-fuel ratio, called the stoichiometric ratio, is about 14.7 to 1.
At that ratio, there's just enough air and fuel for complete combustion.
To maintain the stoichiometric ratio, the PCM determines the mass of the incoming air and then adjusts the amount of fuel delivered by the injector. There are two ways for the PCM to determine the mass of incoming air: the speed density method and the mass airflow method.
So you know what the main fuel system components are for. Let's look at how they work, starting with the TP sensor.
Right. The throttle position sensor is a potentiometer. Its signal reflects operator input. Now, as the throttle plate is opened, the potentiometer's wiper moves up the windings, changing the sensor's resistance and increasing the voltage sent to the PCM. The MAP sensor provides information about manifold vacuum. It's used only on speed density systems.
Since this is a mass airflow system, you won't find a MAP sensor here, but there is a baro sensor, and their operation and output is very similar. The IAT sensor is used in both speed density and mass airflow systems to measure the temperature of the incoming air.
Speed density systems use the IAT sensor's output to determine the density of the incoming air. Mass airflow systems use temperature data to help modify the air-fuel ratio for optimal performance and emission. The mass airflow sensor measures the incoming air mass directly. To do all the tasks involved in measuring airflow directly, it uses lots of internal components.
Speed density and mass airflow systems use the ECT sensor to monitor engine operation. It measures engine coolant temperature and provides a modifying input that helps maintain the air-to-fuel ratio.
The ECT is almost identical to the IAT, but there is one minor difference in construction. There are holes in the tip of the IAT sensor that let air circulate over the thermistor element. The ECT is totally enclosed to protect the sensing element from the engine's coolant. The MAF, baro, and other sensors all help the PCM decide just how much fuel to inject into the cylinders. The fuel injector allows the PCM to control fuel flow. Electronic fuel injectors are really nothing more than solenoid valves. In fact, they're similar in operation to the solenoids used in the anti-lock brake system.
One difference is in the signals that control them.
Which of these waveforms is the normal input to an electronic fuel injector under varying engine speed and load conditions? Select your choice or touch retest to see the waveforms again. Fuel injectors work like any other solenoid valve. An electromagnetic coil lifts the valve head from its seat, allowing pressurized fuel to flow from the injector into the engine. So that's fuel injector operation. Let's look at injector input one more time.
Here, as load increases, injector on time increases to provide more fuel. Which of these waveforms shows injector on time increasing with load? Select your choice or touch retest to see the waveforms again. The final link in fuel control is the O2 sensor.
It measures the oxygen content of the exhaust stream, provides feedback about fuel system performance, and allows the system to go into closed-loop operation.
Now that you know how all the components work, here's a little problem for you to troubleshoot.
Well, that closes the loop on fuel control.
Oh boy, here we go.
Where we pumped up your understanding of stoichiometry.
And covered two different types of fuel control, the speed density system and the mass airflow system.
And a tank full of sensors. Hope you had a gas.
Well, electronic transmission control hasn't reached that level yet.
Right. Robots don't drive them. They build them, but they don't drive them. The fact is, electronically controlled transmissions are very similar to the older automatic transmissions they replace. But electronic control makes them more flexible and more reliable. It also provides some new features that make for smoother shifts, longer wear, and better fuel economy.
After we cover transmissions, we'll spend some time with multiplexing. Multiplexing is a different way to get information from the sensor to the microprocessor. But let's get started with transmissions.
In our first series of exercises, we're going to select electronic control components to replace the mechanical ones used in automatic transmissions for the last 50 years.
50 years? Well, no wonder the components need to be replaced.
By the time we're done, you'll see there's more than one way to build a transmission.
To shift firmly and at the right time, an automatic transmission needs two vital pieces of information: vehicle speed and engine load. In mechanical automatic transmissions, the governor detects speed and controls fluid pressure. In electronic transmissions, the microprocessor monitors vehicle speed and engine load, then controls fluid flow and pressure electronically. But first, it needs information from other electronic components. Which of these configurations could replace the governor's role in measuring vehicle speed? Touch your choices, then touch Done. Well, we've mixed and matched components to detect vehicle speed. Now let's try it with engine load. In mechanical automatic transmissions, the manual throttle valve relays engine load to the valve body. In electronic transmissions, the PCM monitors throttle position and uses solenoids to control fluid flow and pressure accordingly. Which of these components could we use to monitor the position of the throttle plate? When you've completed your choices, select Done. Let's say that the vehicle in which you're installed has just been started for the first time today. Your vehicle speed and engine load indicators tell you it's time to shift from first to second gear. Being the well-programmed processor that you are, you send fluid to the correct solenoids to make that shift. But do you lock the torque converter clutch or leave it unlocked? Now you're cruising in third about a quarter mile from home. Engine load is low and vehicle speed is stable. Would you lock or unlock your torque converter? Soon the engine and transmission are running at normal temperatures. Your driver needs some power and accelerates hard. As the powertrain control module, what would you do now? You've used the torque converter to increase acceleration, and now you're cruising down the road. Vehicle speed is stable and engine load is light. Would you lock the torque converter or leave it unlocked? Let's say it's been a long ride on a hot day. Your driver has just started up a big hill when the transmission oil temperature sensor signals that the transmission is running hot. As the PCM, which signal will you send to the torque converter solenoid?
Not a bad job. Not a bad job at all.
Next, we're going to talk about a new twist in electronic control systems called multiplexing.
We've seen lots of electronically controlled systems so far. Most of them require complex webs of wiring, harnesses, and connectors.
Complex indeed. The wiring on a Taurus is over 17,000 miles long.
Yeah, Bob, that was the wiring on the 747. The wiring on the Taurus is 200 miles long.
Oh, right, yeah.
Right, but despite the fact that you just confused a Taurus with a 747, you do have a good point. You see, all that wiring means complex wiring harnesses and extensive connections. If there were a way to slim down the amount of wiring those systems require, we could make vehicles that were lighter, cheaper, and simpler to repair.
And that's where multiplexing comes in. But before we dive headlong into multiplexing systems, let's review two important concepts: serial and parallel data transmission. Well, you've done a really fine job. You took a whole slew of components and put them into an electronic transmission system while mastering its basic operating principles.
And I especially enjoyed your award-winning role as a powertrain control module.
Oh, yeah. And you've done a great job of covering a very complex subject. Pungal Tilnix.
Multiplexing.
Congratulations, you've completed the course.
Good work. And as usual, you can review any section of the course, or you can exit the course and come back anytime you like. Now, when you return, you'll be able to review any topic in any order. But before you go, would you take a moment to fill out the course evaluation?
And say you like us, because we need the work. Congratulations, you've completed the course.
Good work. And as usual, you can review any section of the course, or you can exit the course and come back anytime you like. Now, when you return, you'll be able to review any topic in any order. But before you go, would you take a moment to fill out the course evaluation?
And say you like us, because we need the work.